Let's take a look at Stapplet.com normal distributions. This is Stapplet.com, and we're looking at the normal distributions calculator. Recently, they added a feature to this calculator that allows for more detailed labeling. So we're going to dive into what this calculator does and how we can use it to provide excellent labeled normal distribution curves that can be used to both find the area under the curve and label it, as well as find values corresponding to given areas. What we see on the screen now at this normal distribution calculator is normal distributions at the top, then an option to change the operation is defaulted to calculate an area under the normal curve, but also has an option for calculate a value corresponding to an area. We'll leave it on the default setting and first use it to calculate area. Next, we have an option for the variable. This defaults to x, just a standard x-axis. However, we can also use this to compare sample means, x bar, differences between two sample means, x bar 1 minus x bar 2, sample proportion, p hat, or the difference between two sample proportions. This is p hat 1 minus p hat 2. And lastly, we have an option for a custom variable. Now, I won't be looking at the difference between sample means or sample proportions here. I'm going to focus on the main tools that we're going to use for Intro to Statistics. Let's start with the variable x. One example that you will see in the homework looks at a population of adults and we plot their systolic blood pressure, SBP, measured in millimeters of mercury, mmHg. So here, this is a great time for this x-axis label input. So right under that variable selection, I will input systolic blood pressure in parentheses mmHg. That's just going to label the x-axis on our completed graph. I did leave the variable set to x. That was the default. This is where we're going to start. Let's suppose this population has a mean of 120 and a standard deviation of 20. These are just made up numbers. It might be in the ballpark, but these should not be used as precise measurements. I've entered those in for the mean and standard deviation and clicked plot distribution. And now we see this bell curve with a numbered x-axis that is labeled with that variable name we put in. And it's always going to draw this with the same relative size and shape. So we're always going to see it centered above the mean with 1, 2, 3 standard deviations to the right and to the left. You can see that in this graph, those are numbered by 20s. So 120 in the middle, 140, 160, 180 to the right, 180, 60 to the left. This is using that standard deviation like a 10-yard marker on a football field, and we're just marking those off to be the same. So you can compare this to a standard normal distribution, which is just a z distribution that has 0 in the middle, 1, 2, 3 standard deviations to the right, and negative 1, 2, and 3 on the left. If we wanted to show a standard normal distribution, we could definitely do that. All we need to do is enter a mean of 0 and a standard deviation of 1, and then we might want to just call this x-axis z. I would recommend changing that custom to z as well. That is only going to be used if we begin plotting points and calculating areas. So let's go back to that example of systolic blood pressure that was measured in millimeters of mercury, and the example I was using had a mean of 120 and a standard deviation of 20. To use this, we scroll down and we see options to calculate the area. We can select between two values. That would be finding a central area. It doesn't necessarily need to be centered, but between two values, for example, if I look at a blood pressure of 130 to 140, then I can calculate that area, 14.99%. It will also give me outputs for z for each of those values. 130 is half a standard deviation above the mean, or 10 points above the mean. That's a z of 0.5, representing that half standard deviation. And the 140 is exactly 1 standard deviation above the mean, so that outputs a z of 1. These are very helpful in helping people to visualize where we're marking on the curve, especially if they cannot see the graph. At one point in time, before we had access to calculators on our phones in our pockets all the time, we actually had tables that would help us to find these percentages based on z, rather than having to plot this every single time. We also have an option to show the labels on the plot. This adds arrows pointing in x equals 130, 140, and the area. If we had a custom variable here, we would see those arrows utilizing that variable. So if I was using a z curve instead, I would want to have it be arrowing in a z and not an x. Okay, well, what happens if we take a sample of 100 people and we get the same mean and same standard deviation? Well, we talk about standard error in statistics. Standard error is standard deviation divided by square root of m. So if we take the standard deviation of 20 divided by square root of 100, well, square root of 100 is just 10, so 20 divided by square root of 100 is 2. Just doing that calculation quickly in Desmos Scientific Calculator is a quick sidestep that we can do to now come back here and reframe this as a sampling distribution. Now the x-axis label could be changed. We are measuring the same variable, but this is actually average systolic blood pressure, and we have millimeters of mercury. That stays the same. We might also add a note. We would say with n equals 100 here. So I'm going to replot that now. I've got additional information included on that x-axis now. And now we're looking at samples compared to samples. So if I wanted to find the proportion of samples between 130 and 140 based on the sample mean, we get essentially 0 of them, because when we take 100 people and average their blood pressure, we only see a standard error of 2 compared to that 20 that we had before. So here it would be more reasonable to be from, say, 121 to 122, putting in those values. That actually will give me the same z-scores as I had before, 0.5 and 1, and the exact same probability. So that shows you how much collecting we do when we collect samples of 100 and average things out. You notice that it's using the X bar to label the axis now. And the other example I wanted to look at is, for example, p hat, sample proportion. We might use that to represent results of a survey. So let's say we take a survey and we get a 60% approval rating. That's going to be 0.6. I'm going to call this approval rating or approval rate on the x-axis. Now to find my standard error here, I need to go back to my Desmos Scientific Calculator. This one is going to be square root of p hat times 1 minus p hat over m. So if my approval rating was 60%, that's my p hat. The complement is 1 minus p hat, that's 0.4. And then I'm just going to highlight the contents of that radical and divide by the value of n. Let's say we've got a sample of 100 here. So with 100 voters, for example, with a 60% approval rating, our standard error is about 0.049, which we can now put in as the standard deviation of this distribution. So I've got my mean of 0.6, standard deviation of 0.049. I'm plotting the variable p hat with an x-axis label of approval rate or approval rating. And now when I plot that, I see what these similar samples would rate at for approval ratings. We can see out to 3 standard deviations on this curve, going out to 0.453 on the left and 0.747 on the right. So a pretty good range of results that could happen with similar samples to this one. These can be used to come up with confidence intervals and things like that. And this is actually a great segue into the second operation. This one is used to calculate values corresponding to areas. So we can use it for left tail. For example, the 70th percentile is a left tail area of 0.7. When I calculate the value there, it's giving me a value of 0.626. So if we had a sample of 100 voters, with a 62.6% approval rating. That would be higher than 70% of samples within this sampling distribution. We might also use it to construct a confidence interval, that is calculating a boundary value for a central area. If I have a confidence level of 0.95, I will put that in, and this gives me the lower and upper bounds of a confidence interval. We can see this confidence interval is entirely above 50%, going from 0.504 to 0.696, which would be good evidence, this sample providing good evidence that the population proportion, or the proportion of all voters, is actually above 50%. We're kind of looking at similar samples, considering sample error, margin of error here. Looks like the margin of error, we tie that to the standard error. And so in this case, we have a margin of error of almost 10%. It's a little bit less than 10% there. So we can use different combinations of these, whether we change the operation, we change the variable. You just want to select the options that is going to really label your work as well as you can, and always make sure that you use the operation as intended. Sometimes you may already know the answer to a problem, so if I put in the values, I could reverse engineer the confidence percentage. It's always good to start with the given information and use this tool to come up with the answers that you're looking for. Those will be very specific then, so we're using a very precise 95% and coming up with very precise interval numbers there.